नहीं, I haven't really heard of him. Karachi se I've just heard of a couple of, no, not a couple, a number of teachers वैसे. Famous ones are Sir Saya, Sir Saad, and Alt Academy वाले भी हैं ना एक सर, क्या नाम है उनका सर, एस से कुछ शुरू होता है, आई थिंक. Yeah, I just know those three, four teachers. Okay. So Sard does not teach at any schools. उन्होंने छोड़ दिया स्कूल सारे. He only teaches online. It's been a couple of years, I think. Okay, everyone, let's begin then. Let's begin. Integration is what we are going to be doing today. We're done with all the concepts. I'll quickly go over everything that we've done until now. And this class is going to be long. It depends on how long you want it to be. I'll be here for as long as you guys have questions. Okay, we want to wrap up integration today. So all the questions that you have, all the problems that you have, make sure that you ask about them today. Okay, there's a start time, but there's no end time for today's class. We will continue for however long is needed. Let me quickly remind you about what we've done until now, the concepts that we have in integration. These functions that are integrated directly, this is given in the formula sheet, right? X power n, e power something, sine, cos, secant squared. In these functions, x can be replaced with any other linear expression, and the rule works like that. That's what we started with. Then these were three differentiation rules that are given in the formula sheet on the differentiation page. We can reverse them to make some integration rules. These are not given on the integration page. You should be able to make them yourself. Okay? This is what we covered. We did some examples on this. Then we looked at the different rules that we have for integrating fractions. We started with the ln rule, where numerator is the derivative of the denominator. How to integrate this? And we had to remember we can only multiply and divide by constants to make it that form, not by x. And tan and cot, they are integrated using the ln rule. You need to remember this. Okay, need to remember that tan and cot are integrated using the ln rule. Then we looked at the tan inverse rule. This is what the rule looks like. The condition for this rule was this. Your fraction should be of this form. Numerator can be any constant. The denominator should have an x squared term plus some constant, right? Then you can use the tan inverse rule in this. We did some examples in this. Then we looked at this next rule, integration using partial fractions, when the denominator is in factorized form, or you can factorize the denominator yourself. Okay, for example, here in this case, we factorized it ourselves and then did partial fractions. There were two specific cases of partial fractions that are directly given in the formula sheet. These two forms, these are given in the formula sheet directly. They integrate like this. They look very similar to tan inverse. The only difference is they have minus in the denominator in place of plus, right? We saw how to integrate these as well directly using the formula sheet. Then the next rule, fraction rule, was this is not a rule as such, just a trick that we use sometimes. Sometimes splitting the numerator makes the integration simpler. These were some examples that we did for that, right? We split the numerator. Then finally, integrating improper fractions. When we have an improper fraction where numerator's degree is greater than or equal to the degree of the denominator, in this case we said, we'll be using long division and break the fraction into quotient plus remainder over divisor, right? That's what we did. All right. Then this was an important thing. In a lot of questions, what happens is in the first part, they give you a function and they ask you to find the derivative of that. And then in the next part, somewhere they require you to use this integration that this result that you got, it integrates back to this thing. And this is something that they use a lot in recent papers. So you need to be familiar with this trick as well. In the first part, they will ask you to find some derivative. And then in the next part, you may have to use the reverse of that in some working. Keep that in mind. Then we did integration by parts, the product rule of integration, right? We saw how this works. We looked at how to decide between u and v dash using I late. And then in that process, we said sometimes we may have to integrate by parts twice. So we integrated once and then it's still a product, but it's simpler than before. So we integrated once more using integration by parts, and then it gives us the final result. You also had to remember that ln x and tan inverse of x, these are both integrated using integration by parts. We write them as one into that, and then when we use integration by parts, ln function and tan inverse function, you need to remember they're integrated using the integration by parts formula. Then the loop method, right? When something does not get simpler, and we try to get the same thing back that we started from, and we use this I and make I the subject, right? We did a couple of examples in this. Then we did integration by substitution. Whenever you have to use a substitution, they give you the substitution in the question, except a couple of cases that we discussed. I'll tell you about them. We looked at this process, right? How to do substitution, how to change the limits in this process as well. And sometimes when you have to switch upper and lower limits, how you can multiply the expression with negative and switch limits using that, right? That's what we covered. Then we talked about how to integrate odd powers of sine, cos, and tan, specifically power 3, sine cube, cos cube, tan cube, how to integrate them, right? Using substitution. So if you have sine cube, we use the substitution u equals cos x. If you have cos cube, we use the substitution u equals sine. And if you have tan cube, we use the substitution u equals tan, right? These are substitutions that you should remember. Then integrating even powers, sine squared, cos squared, tan squared, sine raised to power 4, cos raised to power 4. For even powers of sine and cos, sine squared, cos squared, we said we will be using the double angle identity for cos, right? These forms, so that we can get rid of the power. So we simplify the square and make it power 1, and then we integrate that expression. We looked at these more complicated cases like cos square of 2x, sine square of half x, how to integrate these. If we have tan squared, how do you integrate tan squared? Tan squared is converted to secant squared, and then we integrate that. If we have sine raised to power 4 or cos raised to power 4, we have to use integration. We have to use the double angle identity for cos 2 times on this, right? And then finally, in the last session, we also discussed this extended power rule. This is not explicitly part of your syllabus, but it makes some integrations simpler. So we looked at this as well, how this works. If you have an expression like this, and the derivative of the base is multiplying outside, then the integration is given by just this thing, power increased by 1 and divide by the new power, right? This is also what we discussed in the last session. These were all the concepts that we have done in integration until now. That's pretty much all the concepts, in fact. Now, today we are just going to focus on past paper questions, right? I just gave you a quick review now. Keep the formula sheet in front of you. Keep the formula sheet in front of you as we do these questions, and let me know the problems that you have from the worksheet or from any other papers that you have attempted. We will inshallah do all of them today. Okay, let me know. I don't teach S2, Abhi, unfortunately. Mustafa, you asked me about this as well. I'm very sorry. I was planning that I would start in March. but the schedule has been extremely hectic. I've not been able to get time to, work on resources for that. So unfortunately, no S2 I'm not teaching this year as well. I was planning to, but it's just that I'm not getting any time, unfortunately. Hopefully next year. For the maths S2, both of them are in the pipeline, and then add maths as well, O-level maths as well. There's so much work to do, but not this year, unfortunately. Walaikum assalam. Acha, chale. Let's have a look at these questions then. How many of you have done at least 35 questions from the worksheet that I asked you to do? At least 35 questions? Raise your hands if you've done that. Raise your hands if you have attempted at least 35 questions from the worksheet. Okay. What about the rest of you? You have to do differential equations questions now in the next 3-4 days. And we're starting mechanics and statistics tomorrow as well. Please do not delay things like this. Okay. Achha, let me know the problems that you have then. Let me know the problems that you've got from the worksheet or any from any of the recent papers, and we will discuss them. Okay, challenge. Let's start with this. October, November 2025. Okay, so you don't have a question from worksheet right now. Okay, we'll come back to the worksheet. We will come back to the worksheet. Let's do this question first. Okay. October, November 2025. Let's start with this. Paper 3. Let me see if I have that downloaded. That's this most recent paper. So let me download it quickly. October, November 2025. Paper 3-2. 9709. Okay, let's start with this. This is from the most recent paper that you had, November 2024, paper 3-2. In the first part, they ask you to prove some identity. And then in the next part, they want you to possibly do some integration. Let's check. Okay. Let me copy that here. Question number November 2025, paper 3-2, question number 8. Okay, this is the first part. And the next part is this. Distinction is obviously possible in AS as well as in composite, as in you get full marks, you get distinction. If you also follow instructions, 3 significant figures, etc., in case there are multiple people getting full marks. So yeah, it doesn't make any difference whether you do AS-A2 or composite. You can get it either way. First part, it says prove this identity. Okay, sine 4x is identical to this. We need to prove this. Now, how do we do this? We can start from the left-hand side. The left-hand side is sine 4x. Now, we have talked about how to simplify expressions like these in trigonometry, right? Sine of 4x, how do we simplify this? We can use the double angle identity, or The compound angle identity, both of them work, right? Any of them will work. Sine of 2x plus 2x, we can do it like this. Or sine of 2 into 2x, that also works. What is the compound angle identity for sine? Let's write that down here. Sine A into cos B plus cos A into sine B. It's given in the formula sheet as well. Let's simplify this a bit. What do we get? We get sine 2x into cos 2x plus cos 2x into sine 2x. Now these are both the same, right? Sine 2x, cos 2x, cos 2x, sine 2x. Just the order is different, right? So we can add them up together and that will give us 2 sine 2x into cos 2x. Right? These are both same terms. Okay. Now the final result that we want, that does not have double angles, that has single angles. So we need to simplify this further now. Sine of 2x. Sine of 2x is 2 sine x cos x. And cos of 2x, what about this? Look at the final result that you want. In the final result, you have 1 sine x. You have 1 sine x. You already have 1 sine x here. And the rest of it is just cos. Now for the double angle identity for cos, you've got three possibilities, right? You should be using the one that has only cos because that will be more efficient in this case. Cos 2x, one form of that is 2 cos square x minus 1. It's given in the formula sheet. That will be more efficient to use in this case. So sine 2x, that becomes 2 sine x cos x. What about cos 2x? Cos 2x, one possible way of writing this is 2 cos square x minus 1. Right? So we replace it like this. And now we can simplify this. 2 into 2, that's 4. They've written sin x outside, so I'll write sin x outside as well. This cos x multiply here because they want cos cube x minus cos x inside brackets. I'm multiplying this cos x inside the bracket there. And that will give me 2 cos cube x minus cos x. And that's the same thing as the right hand side. That is what we wanted to prove. Right? That's the first part. This is all that we had to do in this. Make sense? That's the first part. Okay. About topicals, there's no standard rule. There's no standard rule. It varies from topic to topic. So for simpler topics like binomial, partial fractions, 15, 20 questions will be more than enough. For more difficult topics like integration, differential equations, trigonometry, differentiation, complex numbers, you may need to do 40 to 50 minimum. But it varies from person to person as well. The idea is you should be able to do, when you're well prepared, you should be able to do 7, 8 questions in a row consecutively correct. If you're aiming for an A or an A star, that's what I'm talking about. If you're aiming for an A or an A star, you should be able to do 7, 8 consecutive questions, all correct except for maybe a careless error or two, without looking at the notes or the marking scheme. When you can achieve that for a particular topic, then that tells you that you're well prepared and you can move on to the next topic. 7 to 8, relatively more difficult questions, right? Once you can get them right in a row, then you can move on to the next topic. Until you get that, you keep practicing more. Okay? If you're aiming for an A or an A star. Now, if you're aiming for a B, first of all, why? Should be aiming higher. But if you are aiming for a B or you just want to pass with a C maybe, in that case, you'll just change it accordingly, right? Just change it accordingly. So you attempt 7, 8 questions in a row and you say, okay, if you want a B, if you get 6 right, okay, that's sufficient, you can move on. Right? It depends on your situation. So it will vary from person to person. Okay. Let's move on. Part B. It says hence find the exact value of this. Hence find the exact value of this. Integration of this thing, cos cube x into sine of 4x. Cos cube x into sine of 4x. Okay, how do we think about this now? Let me write that down here. Integral of cos cube x into sine of 4x with respect to x. Okay, how do we think about this now? How do we think about this? It's a product. They're saying hence find the exact value of this. Hence find the exact value of this. That means you have to use the previous part somehow. Now, when we integrate something like this, remember what the idea is? We want to get rid of the power somehow, right? We want to get rid of the powers. We've got cos cube here right now. We've got cos cube. Can we get rid of cos cube somehow? Is there a way to get rid of cos cube? Can we do that somehow? If we want to get rid of cos cube, if we could use what we did in the first part, one idea, I'm just thinking out aloud. One way to think about this could be you take sine x to the other side, and that will become 4 sine x in the denominator. And then we add cos x to the other side, that will be multiplying here. That is not going to be any simpler. Okay, so what I'm thinking of is we've got this identity in the first part. What we can say is let's take it to the other side, sine 4x divided by 4 sine x. I'm just thinking if that might help. And then this cos x goes to the other side, becomes plus cos x divided by 2. So that will be 8 here and divided by 2 here. If we replace cos cube x with this, is that going to make things any simpler? Not really. Okay, so that doesn't look like a good idea. Okay, let's see what else we could do. Sine 4x, if we replace that with this, what will that become? Sine x into 2 cos cube x, and okay, let's try doing this and see what this gives us. Cos cube x into 4 sine x into 2 cos cube x minus cos x. Okay, if we do it like this, what does this simplify to? This simplifies to 4 sine cos raised to power 6x minus cos cube sine, and this cos, what does that become? This should have been 8 minus 4 sine x into cos raised to power 4x. This is what we end up getting. Once we get this, this is actually a very useful application of that extended power rule. It's a 5-mark question. If we use this, it will become so much more efficient. We can use the extended power rule here. You see what happens if we do this? We can write it like this: 8 into cos of x whole power 6 into sine x. And the second one, we can write this as 4 cos of x power 4 into sine x. Does that make sense? So I've used that identity first of all. I've used that identity. What I've done is, let me explain this again now. What I've done is I've replaced sine 4x with this whole thing, the identity that we proved in the first part. And then I've simplified this to get this thing. And now both of these expressions that we have got, they can be integrated. They can be integrated using the extended power rule that we discussed yesterday. How do we apply that here on both of them? Let's convert it to the proper form first of all. What is it that we want? What I'll do is I'll break them down into 2 parts. Let's integrate both of them separately. This one separately and this one separately. Okay, what about the first one? We want the derivative of cos outside. Do we have that? Do we have the derivative of cos outside? We have sine. Can we make it negative sine? We can multiply by negative outside. Multiply by negative outside. And inside, we can have cos x power 6 into minus sine x. And now we could say the derivative of this thing is multiplying outside. So the integration is going to be this minus as it is into 8. Add 1 to the power of this. That becomes cos x power 7 divided by 7. This is what we end up getting from this. What about the other integral? We've got minus 4 multiplying outside. What we can do is we can take this negative inside with sign. So we have plus outside. And that will leave us with 4 into cos of x whole power 4 into minus sine x. And now again, the derivative of cos x is multiplying outside. So we could say the integration of this, what is this going to be? 4 remains as it is. We add 1 to the power, so it becomes cos x power 5 divided by 5. That's what the integration turns out to be. Did we have any limits here? 0 to pi over 4. Now we can input those limits, and that's it. That will give us the result. Let's input limits. Limits are from 0 to pi over 4. Let's input those limits. If we input pi over 4, that gives us minus 8 into cos pi over 4 whole raised to power 7 divided by 7 plus 4 cos of pi over 4 raised to power 5 divided by 5. Subtract from this the case when you input x equal to 0, and that will give you minus 8 into cos of 0 whole raised to power 7 divided by 7 plus 4 cos of 0 raised to power 5 divided by 5. Let's simplify this. You want an exact answer at the end. Whenever you want an exact answer at the end, it's necessary to show working. Okay, you need to show working step by step. Cos pi over 4. Put this on your calculator. You'll get under root 2 over 2 from this. Let me just show that to you. Radian, make sure calculator is in radian mode. Cos of pi over 4. Evaluate this. And that will be under root 2 over 2 from your calculator. Okay, input that here. Under root 2 over 2 whole power 7 divided by 7 plus 4 over 5 into cos pi over 4, 4 into under root 2 over 2 whole power 5 divided by 5. Minus and minus, that becomes plus 8 into cos of 0 is 1. You can again evaluate this from a calculator over 7. Minus and plus, that becomes minus 4 into cos of 0, that is just 1, 1 raised to power 5 divided by 5. Now you can simplify this further. Again, do it step by step. Put this thing on your calculator and see what that gives you. Minus 8 over 7. Let's see if we can get an exact answer from the calculator. Otherwise, we'll have to break it down further. Minus 8 over 7 into under root 2 divided by 2 whole raised to power 7. What do we get from this? We are not getting an exact answer from this. We'll have to do it step by step. Let's get rid of 8 over 7 from that. Hopefully that would help. Let's see what this gives us. No, we are still not getting an exact answer. So we'll have to do it a bit manually like this. Let's do it like this. Minus 8 over 7. In the numerator, we've got under root 2, right? So we can write that as 2 raised to power 7 over 2. And in the denominator, we have 2 raised to power 7. So that will simplify to minus 8 over 7. In the denominator, we would have 2 raised to power 7 over 2, right? Something like this. Right? 2 raised to power 7 in the denominator minus the power 7 over 2. This is what we end up getting from this. Similarly here, what we get is 4 over 5 into under root 2 over 2. We can write that as 2 raised to power 5 over 2 in the numerator. In the denominator, 2 raised to power 5. What does that become? 4 over 5. 2 raised to power 5 minus 5 over 2. In the denominator, we would end up getting 2 raised to power 5 over 2 like this. Plus 8 over 7 minus 4 over 5. Okay. Any problems until this point? March paper हो गया already. March paper हो गया already. 5th March. Okay. Gee, what about this? Any problems with this? How do we simplify this further now? It's become quite complicated. Let's simplify this further. Achha, how do we simplify this further? Let me just take LCM of this thing. Or let's take the LCM of the whole thing. We have 7. How do we take LCM? For each factor, we take the highest power, right? 7, highest power of 7 in all of these fractions is 1. So we've got 7 power 1. Highest power of 5 is also 1. So we have 5 power 1. Highest power of 2 in all of these fractions, that's 2 raised to power 7 over 2. So that will be the LCM, 2 raised to power 7 over 2. This is the LCM. That is what we're going to have in the denominator. 35 into 2 raised to power 7 over 2. We can actually evaluate this as well. 2 raised to power 7. So we can, or let's just keep it as it is for now. In the numerator then, minus 8 into 5, that will be minus 40, plus 4 into 7 and another 2 from here. 4 into 7 into 2, that will become 56. And then this one is going to be 8 into 5 into 2 raised to power 7 over 2. What is this going to be? 8 into 5, that's 40. Into 2 raised to power 7 over 2 minus 4 into 7, that's 28 into 2 raised to power 7 over 2. This is what we end up getting, which is pretty weird. Could we simplify this further anyway? Could we simplify the new this power thing somehow? Yeah, we can't use decimals, right? We can't use decimals. We cannot use decimals. That's not allowed. Achha. Okay, let's simplify this a bit further. In the numerator, we get 16. And these two terms are the same, right? 40 minus 28, that will be 12 into 2 raised to power 7 over 2. Divided by 35 into 2 raised to power 7 over 2. And we can leave it as it is. That's our final answer. Now let me just check this as well. What does the marking scheme say about this, the final result? Yeah, that's still going to be the same thing, right? Even if you use square root. Let's quickly look at the marking scheme of this to see how they've simplified it at the end. But this was pretty complicated one, by the way. The integration as well as the final result that we got in exact form. Paper 3-2. Paper 3-2. What was the question number? Fourth last step. Well, actually, yes, you could have possibly left it as something like this as well, right? 8 over 7 minus 4 over 5. But you would have to simplify these two fractions and then maybe leave the other two as it is. Let's just check how much they've simplified in the marking scheme. Question number kya tha? Does anyone remember? Okay. Let's just check if what we are getting is the same thing. 16 plus 12. So they have some a much more simplified form there, right? 1 over 35. Okay, one is a constant, the other term has an under root 2 with that. So let's just check this first. 2 raised to the power 3.5 divided by 35 into 2 raised to the power 3.5. 0.383. That's what we get. Okay, 0.383. And what they have there, 1 over 35 into under root 2 plus 12. Okay, so the result is the same. So this is sufficient. This is fine then. But it could be simplified further. It could be simplified further. Yes. So we could actually simplify it further like this. You see, this is 16, right? 16 could be written as, so that's what's happening. 16 can be written as 2 raised to power 4, right? 2 raised to power 4 divided by 35 into 2 raised to power 3.5 plus 12 into 2 raised to power 7 over 2 or 3.5 divided by 35 into 2 raised to power 3.5. If we break it down like this, these two get cancelled, and this is what we are left with. 2 raised to power 4 minus 2 raised to power 3.5, that becomes under root 2. So that's what they have shown there, under root 2 over 35 plus 12 over 35, right? That's the final answer that you're getting. But this is also fine. This is an exact equivalent. As long as the answer is exact, this is simplified enough as well. This will also be okay. Okay, that's the idea. Pretty complicated. This is the result that we get. Where did 2 raised to power 3.5 go? It got subtracted, right? In the numerator, we had 2 raised to power 4 minus 3.5, so it becomes 2 raised to power 0.5 divided by 35 plus 12 over 35. 2 raised to power 0.5 is the same thing as under root 2. Okay, but it's not necessary that you get exactly the form that they have in the marking scheme, as long as it's equivalent. The question says, the marking scheme says, or exact simplified equivalent. So that's also equivalent. So that's also fine, okay? The expression that we got earlier. Okay, that took too much time. Let's have a look at another. Let's have a look at another. G, any other questions? Chale, let's do this one. Let's do this one. November 21, paper 3-1, question 7, part A. And then we'll do that as well. November 13, question 10, paper 3-1. Okay, we'll do that as well. As long as it's integration, we'll do that. November 21. It might be in the marking and the worksheet as well. Let me quickly check. I'll just open the paper, in fact. November 21, November 21, November 21. Do we have that here? Paper 3-1. Differential equation worksheet is not uploaded. Okay, I'll do that. I'll do that tonight, inshallah. After class, I'll do it. Question number 7, part A. Okay, let's have a look at this. This is differentiation. What's the problem with this? It's a function inside another function, right? How do we differentiate such functions? We start from the outermost function. You apply the rule of this function, right? So it will become 1 over this thing, which is ln x. But then you have to multiply by the derivative of ln x as well. What's the derivative of ln x? 1 over x. That's it, 1 over x into ln x in the denominator. Why was that a problem? Yeah, this is October, November 21. Yeah, this is all that we had to do here. Okay. Achha, let's do that one. Let's do that one. Differential equation we'll be doing in the next class, not today. Differential equation in the next class, inshallah. Not today. Today we're doing integration. All right, let's have a look at one from the worksheet now. Okay, P3 integration worksheet. Okay, let's try this. This is question number 12 from the worksheet. Let's have a look at this. We're going to look at the second part only, okay? The first part is differentiation. You can do that. You have to find the turning point, right? Stationary point. I'm just going to do the second part of this. Let's try this one. What was the question number? 12. Okay, 12, second part. Let's try this. One limit is missing here. No limit was one there. Okay, so it says by using integration by parts, show that for all a greater than 1, this integral is less than 1 over 9. How do we show this? How do we show this? Let's start with this. This is integration by parts. They've given you a hint. Ln x divided by x raised to power 4. We need to integrate this. Limits are from 1 to a. For integration by parts, we need to write it as a product, right? So it becomes ln x into x raised to power negative 4. Ln x into x raised to power negative 4. This is a product. Now, what does the integration by parts rule look like? Integration of uv dash, that is given by uv minus integration of vu dash, right? That's the formula. Use isolate to decide between u and v dash. In isolate, whatever comes on the left, that's u. Whatever comes on the right, that's v dash. We've got a log function and we've got an algebraic function. So algebraic is going to be v dash, right? And log is going to be u. So u equals ln x and v dash equals x raised to power minus 4. Find u dash from this, that will be 1 over x. Find v from this, that will be x power minus 3 divided by minus 3. Okay, this simplifies to minus 1 over 3x cubed. This is your v. Now just input values in the formula. uv minus integration of vu dash. U as it is, that means ln x as it is, into v. What's v? V is minus 1 over 3x cubed. You input that here. Minus 1 over 3x cubed. Minus integration of vu dash. That means v as it is, which is minus 1 over 3x cubed as it is, into u dash, which is 1 over x. Now we need to integrate this thing. Let's simplify this a bit. Minus ln x into 1 over 3x cubed. Minus and minus becomes plus. We can write this 3 outside as well. So 1 over 3. Inside we have x cube and x in the denominator. We can write that as x raised to power negative 4. And that can be integrated directly. So this is what we end up getting, minus ln x into minus ln x into 1 over 3x cubed plus 1 over 3 into integration of this thing, that will be x power minus 3 divided by minus 3. Simplify this further and you get minus ln x times 1 over 3x cubed, or you can just say minus ln x over 3x cubed, right, like this. Minus 1 over 9. So minus is coming from here, right? This is negative power. I'm taking that to the denominator. So it becomes minus 1 over 9x cubed in the denominator. Now this is the integral. They said limits are from 1 to a. Let's input the limits now after simplification. 1 to a. Achha, when we input a, we get minus ln a divided by 3a cubed. minus 1 over 9a cube. Subtract from this the case when you input x equal to 1. What does that give us? Minus ln 1 over 3 into 1 cube minus 1 over 9 into 1 cube. Let's simplify this. The first one gives us minus ln a divided by 3a cube minus 1 over 9a cube. Ln 1 is 0, so this gets eliminated. Minus into minus, that's plus. So we've got plus 1 over 9. This is what we are getting at the end. Minus ln x, minus ln a over 3a cube, minus 1 over 9a cube. And this plus 1 over 9 as well, right? This term, do not forget that. Okay, so that's the integration. This is what we were looking for. Now they're saying show that for all a greater than 1, okay, if a is greater than 1, then this integral is less than 1 over 9. If a is greater than 1, this expression should be less than 1 over 9. How do we show that? How do we show that this is less than 1 over 9? You see, this is the positive term. The other two are negative. We have 1 over 9 minus, let's rearrange them and write them like this. 1 over 9 minus ln a divided by 3a cube minus 1 over 9a cube. 1 over 9, that's a positive number. From this positive number, we are subtracting something. Okay? If we can somehow show that this thing is positive and this thing is positive, then that will ensure that we are subtracting some positive numbers from 1 over 9. So the result is going to be less than 1 over 9. Now, can we be sure about it that these numbers are positive? 1 over 9a cube, this is obvious. If a is greater than 1, then this is definitely a positive number. So this is fine. What about this? Can we be sure that this is a positive number? So denominator is positive 3a cube. What about the numerator? A cannot be negative. So, okay, so a is always positive, but what about ln a? Log of something, can it not be negative? Can log not have a negative value? Remember logarithms? Log can have a negative value. The result from log can be negative. So for example, ln of 0.3, what's that? That's a negative value, right? However, if the number that you're taking log of, that is greater than 1. If you're taking log of a number greater than 1, then that is always positive. So if a is greater than 1, you can say if a is greater than 1, then ln a is going to be a positive number. And if this is positive, this fraction is also positive. So what you're doing is you're subtracting some positive numbers. You're subtracting some positive numbers from 1 over 9. So that shows you that this integral, this whole thing, this is less than 1 over 9, right? You're subtracting something from 1 over 9. So the result that you would get would be less than 1 over 9. Does that make sense? Yes, you can say that ln 1 is 0. So ln of numbers greater than 1, that is positive. Ln of numbers less than 1, that is negative. Yes. Make sense? Okay, let's have a look at another. You guys have no further questions. Are you sure about it? You just want the class to end? 48. Okay, let's try this. Question number 48 from the worksheet. यार ये बेड से ज्यादा जनाजे वाली चारपाई लग रही है मुझे. अस्तगफिरुल्लाह, अस्तगफिरुल्लाह. पढ़ लें कुछ. Aisha, you should actually go and sleep then if you have a paper tomorrow. If you have a P3 tomorrow, then probably it's not a good time to be studying if it's in the morning. 48. Okay, let's try this. Let's try this. Yeah, of course, that's true. This class is more important. That is definitely true. Marks result आपके कहीं पे use तो होना नहीं है तो should be fine. अच्छा. The diagram shows the curve y equals sine x into cos square 2x for x between 0 and pi over 4 and its maximum point m. Using the substitution u equals cos x, find by integration the exact area of the shaded region bounded by the curve on the x-axis. What's the problem with this? What's the problem with this? Don't stress too much about marks, by the way. You should be preparing for Cambridge exams. That's what your target should be. Marks should be taken as practice papers, as in you just work with your time management skills. In the paper, you make sure that you manage your time well. Just get a feel of the exam environment. But don't focus on marks, otherwise you'll just waste this month. Because do you can't do preparation for every exam in 1 day, 2 days. So you'll just be, skimming everything, and that's not going to help eventually. Just go with your plan for the Cambridge exams preparation, and then give marks as they come, just as practice. And pray के exams आपके cancel नहीं हो. I have a better situation geopolitically as compared to what we have right now. Y equals sine x into cos square 2x. Okay, that's the function. We are shown this curve and its maximum point n. Using the substitution u equals cos x, find by integration the exact area of the shaded region. Okay, so substitution that we have to use is u equal to cos x. Now, what do we do when we have to use a substitution? We always, first of all, find the derivative of that. So let's find the derivative of this. Du over dx, what's that going to be? Minus sine x, right? Now, what's the area under the curve? Area under the curve is given by integration of this function, which means sine x into cos square 2x with respect to x. Limits are from 0 to pi over 4. These are the limits. This is the integral that we want to evaluate. And we want an exact area. Remember, we can't use decimals. Okay, now we need to get rid of those dx as well, right? So we make dx the subject in this, and that will give us dx equal to minus du over sine x. Now let's do those substitutions. U equal to cos x. We don't even have a cos x here. So we first of all need to get that cos x. How do we get that? Use the double angle identity for cos. We can use the one that has cos in it. That's 2 cos square x minus 1, right? So I've replaced cos 2x with 2 cos square x minus 1. I can write it like this. Cos square 2x means cos 2x whole squared, right? So what I've done is I've replaced cos 2x with 2 cos square x minus 1. So we still have that square on top of this, right? Into dx. Make sense? So we apply the double angle identity. And it simplifies to this. Now we can do that substitution, replace cos x with u and see what that gives you. Inside the bracket, you get 2u squared minus u whole squared. Replace dx with this thing. And that becomes minus du over sine x. Sin x and sin x, they get cancelled. And this is what we're left with. Now, this is something that we can integrate, right? Integration of this negative, do not forget the negative sign, minus into 2u squared minus 1 whole squared du. This is what we want to integrate now. Now we have converted everything to u. Don't forget to change the limits as well. We will do that. You can't use these limits, right? So we have to change the limits. But how do we integrate this? Can I apply the power rule? Can I apply the power rule directly? Will that work? Power rule, does that work? Okay, power rule. Does that work? It does not work, right? It does not work. Why? Because the expression that is inside, that is not linear. So the power rule does not work directly on this. We would first need to expand it. So let's do that. I can write this minus outside. Or let's just leave it as it is. Minus into, expand this. A minus b whole squared. That becomes a squared minus 2ab plus b squared. So we get 4u raised to power 4 minus 4u squared plus 1 with respect to u. Okay, now what's the integration of this going to be? Minus 4u raised to power 5 over 5 minus into minus, that becomes plus 4u cube over 3 minus u. That's the integration. Now we just have to input limits. Let's change the limits as well now. Clearly write what the lower limit is and what the upper limit is, because sometimes they can be switched. Lower limit is x equal to 0 and the upper limit is x equals pi over 4. Now, what about u? U is equal to cos 0. Cos 0 is 1, so u equals 1. And from here we get u equals cos of pi over 4. And the upper limit turns out to be under root 2 over 2. Now, you see, the lower limit is turning out to be a bigger value. The upper limit is turning out to be a smaller value. So you have 1 here and under root 2 over 2 on top. Now you can keep them as it is and that's okay. There's nothing wrong with this. The upper limit is a smaller number. That's okay. You can just work with it as it is. If you want to, switch limits, you can get rid of this negative sign. Okay, or in this step, multiply everything with negative and then you can switch limits. But it's not necessary that you do that. You can just input limits direct as it is as well, and that's also okay. There's nothing wrong with that. Let's just input as it is. And that will give us 4 into under root 2 over 2 raised to power 5. And we have again got something like that we had before. Divided by 5 plus 4 into u cube. That means under root 2 over 2 whole cube divided by 3 minus under root 2 over 2. This is what we get when we input u equal to under root 2 over 2. And then subtract from this the case when you input u equal to 1, and that will give us minus 4 into 1 raised to power 5 divided by 5 plus 4 into 1 cube divided by 3 minus 1. It's necessary to show this working. You cannot write down the answers directly. That's not allowed. Okay. How do we simplify this now? How do we simplify this? Let's see if the calculator helps this time. Minus 4 into square root of 2 divided by 2 whole raised to power 5. Why is it doing this? So let me just try something else. 2, what if I use power here? Does the calculator help in that case? No. Okay. What I can do is I can simplify this myself. First of all, under root 2 over 2. Under root 2 over 2 could also be thought of as 1 over under root 2, right? Because when you have under root 2 over 2, you can write the denominator as under root 2 into under root 2, right? That's 2. That's going to be 2, right? Under root 2 and under root 2, they get cancelled, and that gives us 1 over under root 2, right? So under root 2 over 2 is the same thing as 1 over under root 2. That will simplify things a little. So it becomes minus 4 into 1 over under root 2 raised to power 5 divided by 5. Similarly here, 4 into 1 over under root 2 raised to power 3 divided by 3 minus 1 over under root 2. This we can keep as it is as well, because we're not multiplying this with anything right now. Then we have minus, that becomes plus 4 over 5 minus 4 over 3 plus 1, right? This is what we get outside. So let's simplify this further. Just remove the brackets from here as well. These are the terms. Now, minus 4, if we write as powers of 2 now, minus 4 can be written as power of 2, right? 4 is 2 squared. This can be written as under root 2 raised to power 5. That's the same thing as saying 2 raised to power 5 over 2, which is 2.5. This is in the denominator. What about this? I can write 4 as a power of 2 as well. So that becomes 2 squared. In the denominator, then I can say 3 into 2 raised to power 3 over 2. Or you can say 2 raised to power 1.5. Right? This is what we get in the denominator. Minus under root 2 over 2. Let's keep it as it is for now. Put this in your calculator. 4 over 5 minus 4 over 3 plus 1. Outside we end up with 7 over 15. ठीक है. अच्छा, अब देखें 2 raised to power 2, 2 raised to power 2.5. What does this become? 2 raised to power 0.5 in the denominator, right? So we get minus 1 over 5 under root 2 plus here as well 2 squared over 2 raised to power 1.5. In the numerator we'll get under root 2, and we have under root 2 over 3 minus under root 2 over 2 plus 7 over 15. This is what we end up getting. Now let's see if the calculator helps now. We can actually rationalize the first one, and that will make things simpler. Minus 1 divided by 5 under root 2. That gives you minus under root 2 over 10. And then you can take LCM, right? So it becomes this. Now you can take LCM of this. Let's see what we get from that. Minus under root 2 over 10 plus under root 2 divided by 3 minus under root 2 divided by 2 plus 7 over 15. And that gives us 7 minus 4 under root 2 divided by 15. And that's our final answer. Does that make sense? Now we can verify our answers, right? Remember how we used to do that? We could verify this answer just by putting in our calculator. Make sure your calculator is in radian mode. Integration function. Just input that function here. Sine of x. This was a 6-mark question. So you can verify our answer quickly. Sine x into cos of 2x and square of that, right? That's how we write this in our calculator. This is the integral cos 2x whole squared. Limits are from 0 to pi divided by 4. This is what we end up getting, 0.089 something. Let's input that fraction now. 7 minus 4 under root 2 divided by 15. And that's also the same thing. That confirms that our answer is correct. Right? So yeah, finally the calculator is of some use. We can verify the answer like this. Right? That's the final answer. Makes sense? Okay. Do you want to do one more question? Enough for today. Okay, differential equations. Now, next class is going to be on differential equations, past paper questions on differential equations. We're done with the concepts. We will most likely have a class over the weekend on differential equations. I want you to have attempted questions on that before that. Should we do Sunday? Will that work for everyone? Or Saturday? Can you do questions before Saturday? Saturday afternoon. So Saturday, let's suppose 2:30, 2:30 p.m. 2:30 to 2:30 p.m. to 4 p.m. Will that work for everyone? Yearly past paper sessions will start from 1st April, inshallah. 1st April. Okay, our M1 and S1 courses are going to end by the first couple of days of April, and then we're going to start past paper sessions from 1st April, inshallah, simultaneously. 2:30 to 3:45. Does that work for everyone? Saturday. That just leaves you with tomorrow to do differential equation questions. Will everyone be able to do that? 25 questions minimum. No, no. Tomorrow we have M1 and S1 classes. We don't have P3 at our regular time now. We don't have P1 and P3 at night now. The 2, 3 classes that we're left with. In fact, for P3 we have 4 classes left, 3 or 4. In one we'll do differential equations, and then two, yeah, 2 is probably going to be sufficient for iteration. 2 for iteration, 1 for differential equations. So at least 3, maybe 4, depends on the questions that you guys have. These classes will be conducted on other days. Iteration's own concepts are straightforward. However, its questions often come along with other topics, and we haven't done sketching of graphs, right? Sketching of secant, cosecant, coit, and cubic functions, exponential function, log function. We have not done the sketching part of any of those, right? So we do that with iteration. So that's going to take time. And its questions are also sometimes a bit complicated. So we will spend some time on doing past paper practice as well. So 2 to 3 classes on iteration, and then 1 on differential equation, in which we do more practice. Okay. Let's do Saturday then. Let's do Saturday. Saturday, no. M1 is 9:50 p.m. and S1 is 11 p.m. M1 is 9:50, S1 is 11. Differential equations class, Monday, 2:30 to 3:45. Everyone here, can you please confirm if that works for you? Everyone in the live class right now? Can everyone confirm? The rest of you as well who have not responded? Saturday, Saturday. Okay, let's do that. Saturday, 2:30 to 3:45 p.m. inshallah. Differential equation questions. Please make sure to attempt at least 25-30 questions before that. Okay, Allah Hafiz. Okay, thank you for reminder again. I'll upload it right now. I'll upload the worksheet right now. Thank you. Allah Hafiz.